Operation Hardtack 1958 encompassed a greater variety of military effects studies than any previous nuclear test series, necessitating the division of the Defense Atomic Support Agency's review of the effects results into 4 films. Part 1 covers basic effects, particularly of megaton devices, and effects on material and structures. Part 2 describes the effects results for the 3 high-altitude shots. Part 3 is devoted to the effects results for underwater tests. Part 4 reviews the effects of sub-kiloton detonations. The introduction of powerful anti-submarine nuclear weapons into the Navy's arsenal posed some critical problems. What are the safe standoff distances for various types of vessels operating in the vicinity of subsurface nuclear weapon detonations? And what are the kill ranges for various types of ships? Some of the answers were on hand. Information gleaned from the 1946 shallow water Crossroads Baker shot. The 1955 Deepwater Wigwam shot, and various high explosive tests. The 1958 underwater testing on Operation Hardtack at the Enewetak Proving Grounds provided supplementary effects data needed to answer naval tactical questions and supplied a host of other vital basic effects information through its 2 underwater tests, the WAHOO deep water shot and the umbrella shallow water detonation. Target ships, along with YC barges, formed platforms for the vast variety of instrumentation to record the basic shock and radiation phenomena. Off Perry Island in Enewetak Lagoon, the fitting out of the heavily instrumented target ships was brought to completion. First came the WAHOO deep water shot, whose surface zero was 8,000 feet outside the lagoon. The 10-kiloton device was placed in water 3,000 feet deep. Downwind from surface zero, the 3 unmanned target destroyers were moored in line, respectively. Several YC barges were interspersed in the destroyer line. The EC-2 target Liberty ship was positioned broadside to surface zero. Target ships had washdown equipment in operation during both shots. The destroyers also had some machinery operating to simulate actual combat conditions. The manned submarine Bonita was submerged at periscope depth. Further out were a number of active manned ships, including the submarine Sterlet. H-hour for the deepwater shot was 1330 on 16 May. For the umbrella shallow water shot, the array was moved inside Enewetak Lagoon. H-hour for the shallow water shot was 1115 9 June. For the underwater pressure effect studies, strings of mechanical and electronic pressure time gauges, as well as ball pressure gauges, were suspended from target ships and barges. On the deep water shot, some strings were suspended to depths of 2,000 feet. On the deep water shot, the variation of peak pressures with range expected for isovelocity water conditions are indicated by this curve. Actual measurements varied from 1,840 psi near the 2,000-foot range to 45 psi at 15,000-foot range. The increasing deviation of the two curves with range is due to refraction of the shock wave. The close agreement at short range confirms the isovelocity formula developed from wigwam data, which gave the free water curves. The detailed effects of refraction on the shot are under study by several laboratories. Two other underwater studies are here treated briefly. Hydrodynamic yield experimentation to measure the shock wave velocity at early times was attempted on both shots. On WAHOO, the tests were unsuccessful, chiefly due to the lack of a stable platform. On the shallow water shot, telemetered data was obtained from two strings of blast switches, showing an effective hydrodynamic yield of about 10 kilotons. However, pressure distance curves from which hydrodynamic yields are determined showed an as yet unexplained deviation from the slope expected as a result of wigwam studies. One post-shot study was the measurement of the shallow water shot crater. It measured 20 feet in depth, 1,500 feet in diameter, with no crater lip. The underwater pressure and shock results were closely tied in with the ship hull and machinery loading and response studies. For the hull studies, a great variety of gauges were installed on the target vessels to record phenomena on velocities, displacements, deflections, pressure, strains, rolling, and pitching. There was no hull damage to the target destroyers on either shot. Damage from the two shots to the EC-2 merchant ship hull was light, much less than expected. Although the hull suffered cracking and plastic deformation, the inner bottom was not damaged. For that portion of the testing devoted to shock response and damage to critical ship machinery and equipment, several hundred instruments and self-recording shock spectrum gauges were used, along with 40 high-speed motion picture cameras. On the deep water shot, damage to the destroyer propulsion and auxiliary machinery was negligible. On the shallow water shot, the closest destroyer suffered enough machinery damage to make continued operation questionable. Damage on the other two destroyers was minor. The EC-2 received crippling damage to machinery and equipment. As with the destroyers, the hull alone could take more shock and pressure than the machinery and equipment. One word of caution. All figures throughout this report refer to results obtained under the WAHOO and umbrella conditions. That is, shot yield and geometry, oceanographic conditions, and ship types involved. Now we will consider the submarine on which data was obtained to determine lethal damage ranges to hulls and equipment. Instrumentation included strain, pressure, and deflection gauges, along with high-speed cameras and roll, depth, and flooding indicators. A squaw 4/5 scale submarine model hull of the SS-563 class was positioned with instrumentation similar to that used in the squaw on Operation Wigwam. The Bonita received no permanent hull deformations on either shot. Its minimum safe standoff range for the deep water conditions was not directly obtained. Two other underwater response studies were made, both on minefields. One experiment studied the effectiveness of minefield clearance by nuclear weapons. The other mine experiment, also conducted on the shallow water shot, was concerned with the mine actuating influences of nuclear weapons. Some data were obtained, but further study will be necessary to predict the pressure, acoustic, and magnetic effects on the mines. We will now examine the WAHOO and umbrella studies on visible surface phenomena, the dimensions and extent of spray domes, base surge, and water waves. On the deep water WAHOO shot, the rounded spray dome rose to 900 feet. This was immediately followed by a bubble pulse, which sent numerous water plumes in a spherical pattern to a height of 1,750 feet. A base surge developed at around 30 seconds and spread out rapidly to about 7,000 feet in crosswind radius and well over 1,000 feet in height at 2 minutes. The surge was irregular in size and consistency. It was carried downwind beyond the target ships and was barely visible at 12 minutes after the burst. Water waves from WAHOO almost doubled in height as they approached nearby islands, raising the water level some 12 feet over the closest island. On the shallow water shot, the spray dome developed rapidly into a columnar plume, attaining a height of 5,800 feet. Except for a tenuous mist at the center, all visible material fell back into the water or the base surge, which appeared in about 13 seconds. At 75 seconds, the surge was about 1,850 feet high, and at 7 minutes, its crosswind radius was around 9,500 feet. Wave heights on the shallow water shot agreed with predictions. At 1,500 feet, the crest of the first wave extended 22 feet above the following trough. Beyond 6,000 feet, this highest crest had moved back in the wave train. Shoaling water and coral heads broke the wave up and made inundation of nearby islands negligible. Air overpressures, a determining factor in the use of aircraft for nuclear attacks against enemy submarines, were measured on both underwater shots. Shockwave pressure pickups were suspended from balloons and shipboard mounts on both shots. In addition, on the shallow water shot, 32 rockets deployed the parachute-borne pressure gauges to various heights up to 15,000 feet. On both shots, peak overpressures at low levels agreed well with predictions. On umbrella, overpressures at levels above 1,000 feet were generally lower than expected. Maximum pressure recorded was 1.88 psi, this at 2,500 feet altitude on the shallow water shot at a range of 2,000 feet. This concludes results of the blast and ship response experimentation. Equally extensive were the radiation tests on the two shots, both on basic phenomena and on shipboard vulnerability studies. These 9-foot diameter coracles contained instruments which documented the radiological environment resulting from the WAHOO and umbrella detonations. For WAHOO, 21 coracles were spotted throughout the target array, mostly downwind, moored to the ocean floor, some to a depth greater than 6,000 feet. 26 coracles were placed for the umbrella shot, 5 deep moored outside the lagoon, the others within the lagoon. Each coracle mounted a specially developed gamma intensity time recorder to define the local gamma field with respect to time. The coracles also housed incremental collectors which sampled the radioactive debris deposited at the coracle position. Some contained probes to measure water radiation levels. Supplementing the coracle assemblies were several score floating film packs dropped over the target array prior to and after zero time to collect total gamma dose data to assist in drawing up dose field contours. Combined results of both shots showed that almost all of the gamma dose occurred within 15 minutes after zero time and was due to the passage of airborne radioactive material. In the shipboard radiation vulnerability study, gamma intensity time recorders of both the unshielded and directionally shielded types were used to document gamma radiation phenomena aboard the target destroyers, both on deck and in compartments. Hundreds of film badges were also placed all over the ships. Transit radiation, that is, the cloud and passage of the base surge, contributed practically all of the total dose aboard the ships. The underwater dose and the deposited ship contamination were insignificant. On both WAHOO and Umbrella, 4 compartments of Destroyer 592 were instrumented with surface samplers, total and time incremental air samplers, gamma intensity time recorders, and animals. Airflow rates for ventilation and boiler combustion were controlled to represent conditions during nuclear attack. Early analysis of the exposed animal data and that from the mechanical samplers on the deep water shot at the 592's range, 4,900 feet, indicated that the dose to personnel inside the ship was generally below the threshold of acute exposure, but that long-term effects might be produced. On the shallow water shot at the 592's range, 3,000 feet, no inhalation hazard capable of producing either acute or chronic effects existed, except possibly chronic effects might result from exposures sustained in the engine room. The washdown systems reduced the fallout contamination by 95%. In summing up, one conclusion towers over all the other underwater test findings on safe standoff ranges. This conclusion is that under the conditions of these tests, radiation dangers dictate ship locations far beyond their hull and equipment shock limit capabilities. The 2 underwater shots on Operation HARDTACK extended our knowledge of nuclear underwater blast, shock, and radiation effects. A great deal of information was gained, which upon completion of analysis will help to provide answers to naval tactical problems.